In this presentation, we're going to look at the physical properties of metals, ionic compounds, and covalent compounds by looking at their structure and bonding. Of course, the structure of metals is always a giant metallic lattice, and the bonding is metallic bonding. The structure of ionic compounds is always a giant ionic lattice, and the bonding is ionic. For covalent compounds, they can be giant molecular structure, such as you have in diamond or graphite, or simple molecular structure. And the factors which determine the strength of the bonding in metals is the number of valence electrons and the size of the cation. I've mentioned this in a previous presentation, that as the number of valence electrons increases, the strength of the metallic bond increases. And also, as the size of the cation increases, this will cause the metallic bond strength to get less. For ionic bonding, the strength of the bonding really is due to something called charge density. The larger the cation, the lower the charge density. So if the ions get large, the strength of the ionic bond gets less. And also, as the charge of the ions increases, the ionic bond strength will increase. For covalent compounds, if you have a giant covalent compound, it will have a very high melting point because you've got to break covalent bonds. The bonding is covalent bonding. Whereas for simple molecular structure, the bonding is the intermolecular bonding. So therefore, the melting point is much less, because all we have to break are the the intermolecular bonds. So these are the things we're going to look at today. Relate physical properties of matter to differences in strength of forces of attraction. So variation of melting points, boiling points, and solubilities, and conduct melting point and boiling point determinations, and solubilities in polar and non-polar solvents, and electrical conductivity, and illustrate practically the properties of ionic and covalent compounds. We're going to do that in a practical class, and explain the formation of the following: ionic bonds, kind of done that already, covalent bonds and metallic bonds. And covalent bonds are going to be discussed in terms of overlap between orbitals, which can be sigma bonds or pi bonds. I'm going to mention those. Metallic we've already looked at. So, giant metallic structure. These form metals. For ionic compounds, these are formed between a metal and a non-metal. And giant covalent structure. I can think mainly of group 4 compounds, graphite, diamond, and silicon, and silicon dioxide. Simple molecular or non-metals, HCl, H2O, methanol, etc. Examples of metals, of course, are sodium, iron, copper. So as noticed, sodium is a fairly soft metal because the metallic bonding is weak, whereas iron is very strong. And sodium has a fairly low melting point. Ionic compounds, think of sodium chloride, for example. particles at the lattice point, you have positive metal ions in metals. Remember, they're surrounded by a sea of negative electrons. Ionic compounds have positive and negative ions. Giant covalent structure, you have atoms, which are held together by covalent bonds, or simple molecules. The particles are the molecules themselves, not the atoms. The molecules will form the particles. Bonding. For metals, metallic bond strength. You have an electrostatic bond between metal ions and the delocalized electrons. And as the number of valence electrons increases and the charge of the positive metals increases, the number of delocalized electrons increases, and the strength of the metallic bond increases. And metal ions smaller, positive nuclei closer to the electrons, and therefore a greater electrostatic force between the positive nuclei and the delocalized electrons. They have stronger metallic bonds. In the case of ionic bonding, you have attraction between positive ions and negative ions. Important point is every sodium ion is surrounded by 6 chloride ions, and every chloride ion is surrounded by 6 sodium ions. The giant crystal lattices form a 3D regular packing of positive and negative ions. We've discussed this already. For a giant covalent structure, the particles, we're thinking about atoms, and these are held together by strong covalent bonds. I suppose for things like carbon, you can think of graphite and diamond as two allotropes. There are other allotropes as well, such as buckminster fullerene, but we're not going to go into that today. And then you have, diamond and graphite, tetrahedral arrangement of each carbon or silicon atom joined to 4 other carbon atoms in diamond. In silicon dioxide, silicon each bonded to 4 oxygen atoms. And in graphite, the carbon atoms are hexagonally arranged into layers, and you can see this here. And the layers are held together by weak van der Waals forces, and the layers therefore easily slide over each other, and this makes graphite a good lubricant. What about simple molecular structure, such as HCl, H2O, or methanol? You have simple discrete molecules, and atoms are held together by strong bonds in molecules, and molecules are held by weak intermolecular forces. So you can see this in the case of, this is a dimolecular substance, maybe hydrogen or something. And then you have water. Van der Waals forces, hydrogen bonds, form between molecules that contain hydrogen that bonded to nitrogen, oxygen, or fluorine. And that basically, and this illustrates the sigma bond and the pi bond. So you have different types of bond that can form. Sigma bonds will form when you have two s orbitals overlapping, or an s and a p, or 2 p's. And all of these form a sigma bond. And when 2 p orbitals overlap this way, you form a pi bond. And these are going to be discussed in more detail in the subsequent class. And this finishes this fairly brief presentation.